giving the keynote talk. Eitan Yacobi did his undergrad here, right? First degree in computer science and mathematics at the Technion, also his master. He did his PhD in University of San Diego and a postdoc at Caltech, and he's an assistant professor in the CS department. Welcome. How does it work? Oh, or that, okay. Okay. Boker Tov, good morning, everybody. And thank you, Chaim, for the nice introduction. He asked me if, how I want to be introduced. So I figured I'll do the same thing as Shlomo did, just to say that I'm a professor over here and what time I joined. But you did everything okay, but I was hoping you're going to say one more thing and learn from Gerhard from yesterday and just say I'm an assistant professor and you heard that I'm going to get tenured. So I lost my window of opportunity, I guess. So I might be on the market very soon. So, okay. So I'll talk about private information retrieval, and I'll try to tell you what has been done pretty much, especially in the IT community for the past 4 or 5 years in this area, because this problem has been suggested and mostly started from the CS department, from the CS theory side. However, it shifted in the past 5 years towards IT, and we'll see why and what's the differences between the more practical IT people compared to the CS theory folks. So let me first tell you what is a private information retrieval. So the setup is relatively simple. You have some database, and the database has, say, n bits, and let's talk about just bits for now. You might argue about it, but so Alice wants to read, say, bit number 98. Good, so you have the database has many bits. So she wants to ask some queries to the database, and so this is the information retrieval. She wants to know what bit number 98 is. The private is database should know nothing about bit number 98. Database should deduce even that it's not even bit number 99. So everything has to be fully secured in the sense that from the database perspective, it can deduce nothing about what bit Alice wanted to read. So if you think about a naive solution to this problem, and if I'm Alice and I want to make sure that the database would know nothing, and database is a reliable one, so I can ask whatever I want, he will respond back, which is good. So I can just, what I can do as a naive solution is just read the entire database. So if you have 1 million bits, I'm going to download all 1 million bits. Database can deduce nothing because I will do the same strategy for every bit that I want to read. So this is fully secure. However, the main problem is how do you improve the communication complexity? And however, if you have only one database, if you have one server that stores the database, you cannot do better than this. So that has been shown and proved. So it becomes more interesting when you have the database stored in more than one server. So you have some copies of the database, and you can communicate with both of them. Let's assume for now that they do not collude. Otherwise, it would be as one server. And there are basically two models. The one from the information theoretic PIR, so you want it to be fully secured in the information theory perspective, or you can also think about computational PIR. So under the same constraint and restrictions, so limited power computation power that you have, you still want it to be secured. But in this talk, I'll talk only about information theoretic PIR. So let's see an example how you can actually do better than download everything if I am going to have more than one copy for the database. So I'll start with a very simple example. Say that we have two servers storing the database, and Alice wants to read bit number, again, 98. So she's going to choose some random vector. Let's call it A over here. And then she's going to transmit A to server number 1. So this is just random vector. Their server can deduce nothing. And she's almost sending the same vector to the second server, so just flipping bit number 98. So for the say, it's still because A is random, A and shifting the 98th bit still become a random vector. So she's sending this one to the second server, which is great. Now, what every server needs to do is very simple. It's just to take an inner product between the vector and the database. So database, we said it's still only on bits. And they get like 1 million bits, random one. They take the inner product between the vector and the database. So each server responds with a single bit. So the nice thing is, if we go, because we flip the 98th bit between the two vectors, what Alice can compute, if you take the 2 bits and take their sum, their XOR, she get exactly bit number 98. So this is nice and cute. It's a really nice example. I guess I was able to convince you that indeed it works. In terms of communication complexity, so the download is great. We only got 2 bits from the 2 servers together, but for the upload, we upload like 2 n bits. So I might as well just download the entire n bits from one of the servers and actually do better than this. But I didn't waste your time for nothing. You'll see why actually this example is still important when under what cases. So again, so this problem first arises in 95 from the CS theory side. And just to be a little bit more formal, what's the definition over here? So we're going to have K servers at the beginning, and each one of them stores the entire database. So it's a full replication system that you have. Alex wants to retrieve bit number 98 without revealing any information on this, the index of this bit. And this protocol consists of 3 parts. So the first part is for Alice to do something randomly, to choose these queries, send the queries to the servers. So this is the first part. Second part is every server has some function that he needs to compute based on its identity, because maybe different servers can compute different things, and also based on the server that he has and the query that he got. Great. So then Alice gets, this is the second algorithm, and then eventually Alice gets all the responses, and she needs to do something in order to retrieve the bit that she wanted to read. So this is like formally how the setup works. What you need to require over here, the first one is privacy. So each server can deduce nothing about the bit that Alice wanted to read, and clearly that this is correct, and this is correct worst case. In terms of figure of merits, the communication complexity was the main thing that the CS theory wanted to improve over here, and I'll talk about it. And then storage overhead is also what happens if you don't want to do actually just replication. Because the first problem came with full replication, but if you can think about any coded setup over the servers, then this problem is also interesting. Great. So let me show you like another example that started from the same work. So this is started with Shor Kushilevitz Goldreich in Sudan in 95 when they first proposed the problem. And so they gave up this, the first example was nice, and they say, hey, you can do better in the download, not in the upload, because you still have to upload 2 n bits. But let's modify this example a little bit. So if I'm going to talk about all of my bits, now let's put them in a 2-dimensional array. So it's square root by square root of n over here. And it's now the same thing. Alice wants to read like one of the bits. So every bit now has 2 indices for the row and the column. This is what she wants to read. And they said, okay, let's do a similar thing. Instead of choosing one random vector, now they're going to choose two random vectors, and each one of them of size square root of n. So basically one random vector for the rows and another one just for the columns. And so in this example over here, they use it for 4 servers. And with 4 servers, so the first server gets these 2 random vectors, A and B, each one of them of size square root of n, one for the rows, one for the columns. For the second server, just flip one of the bits of the rows. The third one, you flip one of the bits of the columns. And then the fourth one, you flip both of the bits. So I'm not going to go this math, but it's a nice exercise just to verify that indeed each server gets these two vectors, and it responds with a single bit. And yet it's possible for Alice to get all 4 bits, and it's like the same trick, and you get the bits that she wanted to read. So this is great, because now they're able to improve the communication complexity from order of n to order of a square root of n. However, this one requires 4 servers. But there's a really nice example, another idea how to do it using covering codes. And actually with 2 servers, they were able to go to n of 1/3. So it's in before that they had 4 servers, square root of n. Now they were able to do it with 2 servers with complexity of n to 1 over 3. And the idea in the previous example, the upload was still high, the download was relatively low because every server had to respond with a single bit. But if you wanted to be symmetric, so both the upload and download would be the same amount, then it was possible to go to n to 1 over 3. And this is in general case what happens. So this problem was actually open for 20 years in the sense with 2 servers, whether it's possible to improve to the n of 1 over 3. And there are a lot of works, and also it depends also on the number of servers that you have. So a lot of work from the CS theory side that they are able to improve up to replication 3 to have a complexity where the power of n goes to 0 with n. But for 2 servers, it was actually open for 20 years how to improve the n of 1 over 3. And so basically the last result that came from that side is the one from Devere and Gopi, that they're able to, the communication complexity you see over here is a subpolynomial with n. So you have n to the power over here goes to 0 with n. And that was a complete breakthrough because it really improved and it solved one of the most important open problems in this area. I'll just mention that the lower bound is still open in terms of how much bits you have to communicate, and this is order of log n. So there is still like a gap over here, which is significant one, but this becomes even more challenging how to close on this gap. But so that's basically the bottom line here, that if you have two servers, then it's possible to have a subpolynomial communication in terms of upload and download. So this is kind of like what has been done from the CS side. So this problem shifted a little bit. It shifted in the past 5 years to the IT community. And then I mean, it's all good. I mean, we had this really nice example with 2 servers, and you communicate, and it's all great. But in real life, the database doesn't really store bits. The database has files. So every file would be 1 megabyte, 1 gigabyte, or even more than that. So it's still possible. Now let's say that instead of database storing a bit for every file, now I'm going to have a file. So this F is going to be really, really large, like let's say 1 gig. So it's still possible to do the same thing. But if I'm doing the same thing, what Alice needs to generate is still a random vector of length n bits. I don't need to work over files. Because if I'm going to get the first vector A and then flip the 98th bit for the second server, we can still do the same thing, but instead of just working over the bits, working over the files. And eventually, every server is going to respond with a single file. And what Alice needs to do is take the XOR of these 2 files together, and then she gets exactly the file that she wanted to read. And the security, the privacy, everything works here in the same way. So this is great, because now the download is 2F bits. What we download is only 2 files, which is great. The upload is 2N bits. But so let's say that you have a big database. It has like 1 million files, or even more than that, 1 billion. So you still have to upload like 1 million bits or even like billion. This is basically nothing. If you need to download like 1 tera or 1 gig, you can see what the orders of magnitude over here. And so for every practical reason, the size of the database is significantly smaller than the size of the file. And if that happens, then you don't really care about the communication complexity in terms of both upload and download. What actually is more important is to look at what's the communication complexity from the download point of view. And you can see from the download point of view, even with two servers over here, we're able to download only 2 files in order to read 1 file. So this is great. I mean, in terms of rate, it's 1/2. The question is, now I can ask, okay, can we actually do better than this? Can I download less than 2 files in order to retrieve 1 file privately? And the answer is yeah, it's possible. It's like asymptotically possible. But this is, for every practical reason, an optimal scheme for 2 servers. But you can extend it. Now you can ask the same thing. Okay, what can we do if I'm going to have 3 or more when I care from now on only about the download complexity? And also, let's say that you store the files in any, say, MDS code or any coded setup over the servers, which is now commonly used for any distributed storage system. So now you can ask the same thing. Well, what is basically the best I can do in terms of the download complexity when Alice wants to retrieve one of the files? So this is basically another interesting question. What is the gain when you have coded PIR schemes? Another thing also to take into account is maybe some servers are going to collude. So another dimension of this problem is to do the same thing. Let's say I'm going to have 10 servers, but every 2 of them can collude, and we still want to be private against this kind of setup. Okay, so let's give you like just one example how things could work in a coded setup. So now let's say that you have a database and it has n bits. So one example is, or n files. One example is to store half of the files in one of the servers, the other half in the second server, and then the third one is just going to store the XOR, the sum of these 2 parts. And so in this case, we improve the storage overhead. Instead of factor of 2, it's a factor of 1.5. Great. And it's still possible to do similar tricks. So you're going to send, like, take one random vector, send it to one of the servers, flip the bit that Alice wanted to read in both of them, do the same thing, and then again you get the file or the bit. So it works whether the database is bits or files. Okay, so this basically example was then extended for other MDS. I mean, what I showed over here, it's another example of MDS code, but this has been extended by Razan Tajlin and Salim El-Ruhaib in 2016 to do it for arbitrary MDS code. And for arbitrary MDS code, then you also, in terms of what I discussed up until now, it's like we want to look at what they call the PIR rate. So PIR rate is, I just want to take the ratio between the size of the file, how many bits Alice wants to read, and by the how many bits we had to download. And this is called the PIR rate. So in the first example that I had with the two servers, then the PIR rate was 1/2. In the 3-server example that I just had, so every server needs to respond with 1 file, so the PIR rate was 1/3. And in general, if you want to ask what is the best PIR rate, this is what's called the PIR capacity. So the PIR capacity is what the best you can do. You can say if the number of files goes to infinity or not, but it's basically building a scheme which is optimal. And you can talk here about both the epsilon capacity and the 0 error capacity. So 0 error, we want to make sure everything works. Worst case, epsilon error, you want to allow some error probability that it diminishes to 0. Okay, so just a little bit what Salim has done with his student Razan in 2016. They say, okay, now we can do the same thing. Let's say that we use an MDS code. And in this example, I'm going to use the 4.2 MDS code. So if it's a 4.2 MDS code, what you can do is you take every file, you partition into 2 symbols. You can work every extension field over here. Here it has to be at least a field of size 3 because it's an MDS code. And then you take the file, you partition into 2 parts, and then you have 2 more redundancy parts. So this is what you store in the 4 servers. And then it's basically the same family of ideas and protocols. Alice needs to choose randomly 2 vectors, 1 vector, sorry, A, and then she's sending A to the first 2 servers, and then she flips the 98th bit or the symbol to the 3rd and the 4th. And again, following the same ideas, she can then retrieve the file that she wanted to read, and everything remains private because every server still gets an arbitrary file, a random one. Okay, so let me go over kind of like what has been done. So now we do like a fast forward for the rest of the work from the IT part. And really what the interesting part was, what is the capacity? So if I'm going to tell you that we use an MDS code, it could also be like a repetition code. So basically, we're interested to know what is the MDS code that you use, whether you don't allow colluding servers, and the question is, what should be the PIR capacity? And so Sunan Jafar promoted all of this part of this work, and so for let's say first they discussed about the case that you have full replication, and they wanted to know what is the maximum PIR rate, the capacity, when you have full replication. And I told you that the case of replication 2, the PIR rate was 1/2, but it's not strictly optimal. And so n is the number of copies, the number of servers that you have. And if I put like n equal to 2 over here, you can see that the capacity approaches to 1/2, but it's strictly below that. So if you allow some sub-packetization, then it's possible to achieve exactly what the PIR capacity is. And again, it goes to 1/2 or 2, but you can do slightly better than this. And then they extended this one. Same setup. You have it's a full replication, but you have some servers that can collude. So T is the number of servers that can collude. If you put T equal to 1, you get the same formula over here. And so this is what has been done. And then Shanur did with her student, Bana1. See, this is the same thing, but for coded setup. So R over here, it's the rate of the MDS code that you use. And if you have replication, it's just 1 over n. So then we get exactly the same formula as over here. So this is also has been done. And then you have some more extensions. So they have some more extension in the sense if the size of the messages could be arbitrary, or it's also a good question, what happens if you allow multi-round? So multi-round is I can ask the first server something, he responds back. Based on the response, then I can ask the second server something and then get the response. And the question is whether multi-rounds can or cannot improve the PIR rate. And it's a nice actually observation that they had over here. It's still basically open, that if you just have like full replication, multi-round cannot improve the capacity. But if you allow to do a coded setup, if it's not a replication, then it's possible to do better. But it's only from the theory point of view that just show how it's possible to do, but it didn't really give you an explicit way how to do it. Okay, so then one of the parts which remained open up to that point, so I said, so now you can do coded setup, you can also have colluding, but the case of having both coalitions with a coded setup has been open for like the past 2 or 3 years, but this problem has also resolved in the past year, and they also managed to extend basically these formulas for the case of colluding servers with a coded setup. Another dimension is how to do a multi-message. So if Alice, for example, wants to read more than a single file, so this is what also what happens. So this one are more information theoretical result in terms of capacity, but there is also the other dimension of building like a specific and explicit code construction and protocols. And this also works whether it depends if the size of the file could be arbitrarily large, so then you can have any subpacketization, or if you also want to restrict the size of the file, and then the subpacketization is also a constraint. And so I'll not go over all the details over here, but basically there are several approaches taking into account what kind of code you use over the servers and whether or not you want to talk about colluding servers or whether or not you want to read more than a single file and so on. And even in the past year and a half, so this basically is up until roughly 2017, I'm trying to be up to date, but if you randomly open the archive, you always see like at least one paper on PIR nowadays. So it has been studied. There are many more cases. If you mention like multi-message, there is also PIR with side information. So if, for example, Alice already has some information on the files in the database, and she still wants to retrieve some information, how that helps. I talk about when the servers store the files in an MDS code, but it doesn't have to be an MDS code. So it could be like LRC code or any other kind of code, and the question is also, it's even a question whether MDS code is optimal in terms of improving having like the best PIR rate. Functional PIR is something which I want to elaborate more now, but it's the idea that Alice wants to not retrieve one of the bits, but maybe some linear combinations of the bits or the file, or maybe some other functions. And some other function, it's actually interesting because, so the basic question from the information retrieval that has been proposed from the beginning is, it's a very basic one. Alice wants to read the file number 98. But if you think about information retrieval, it's not just this. Information retrieval is very wide, and you can ask like many more questions when you have a database, and maybe you want to ask even some more questions which have some more meaning. It's not just like an identity of one of the files. Maybe Alice wants to know some function, I said, but not even linear function. Maybe something where has some more semantic into it, that like something, what is the maximum file, minimum file, or if Alice has some information, maybe she wants to know what is close to her information. And so this is basically another setup of dimensions of work, and this is what we've been mostly working lately. So I'll tell you what we've been doing on this problem. This is what we call private proximity retrieval. And so it's very similar to PIR, but now we want to slightly change what Alice wants to retrieve. And I change a little bit the notations over here just in terms of convenience. So I apologize for this, but now the number of servers is going to be capital N over here, and we have the database, again, storing, let's say, 1 million files. But now the difference is Alice doesn't want to read just like one of the files. Alice has some information. She has a file, and she wants to know, for now, say, all the indices of the files or the other records which are close to her file. Okay, so maybe think about Alice has some location, and all other files are locations of some other agents or friends, people like in the, even like as a group. And she just she doesn't care about, agent number 98 where location is. She has some current location, and she just wants to know what other agents are close to her location. Okay. So that's basically the setup. I'll give some more example. But this is basically what she wants to know. So basic thing about the agents, like over here at some other points, she's sitting over here, and she just wants to know who is close to her. But now we'll not be able to do like full privacy, but we want to have the scheme to be as private as possible. But just to be formulas over here, so it's basically the same setup. She needs to generate with some randomness queries over here, and every server is going to respond with an answer. And what she wants to calculate is an approximation. Maybe she can do exactly to know, she set up some distance, and maybe she is able to know exactly which agents are close up to a certain distance, or maybe an approximation for this problem. So the figure of merits which we care at this point is, one is the privacy. So we don't require full privacy because it's not possible to achieve full privacy over here. And also the distortion. So distortion is, maybe she wants up to radius, say like 5, but based on all of the replies, she was not able. But maybe she is able to make sure every agent which is distance of to most 4, she's able to know. And maybe there is some error, so maybe she also got a response for another agent which is of distance 6, but she wanted to know only up to 5. So this like a epsilon 1, epsilon 2 over here tells you where you can bound the answers of what you got from all the servers. And I'll just mention, so this is a joint work with Tuvi and Yue, who is our postdoc here at the department, and together with Oliver Gnilke from Aalto University of Finland, and Dave Karpuk, who is in Bogota in Colombia as an assistant professor over there. So this is what we've been mostly working for the past year. And just a little bit of some more basically motivation. So again, one of the motivation was what's called a private proximity testing. So this is even like a cellular network or any kind of network that you want to have. And I have a location and I want to know whether it's a group or if you want to have another person, and we just want to know whether we're close to each other. But none of us want to expose, for obvious reasons, what the current location is. Some other one, this is more for the machine learning setup or similar one, when you want to know the problem of the k nearest neighbor problem. So this is similar setup. You have some file or anything, and then you have some distortion measure or some any distance function that you have, and you just want to know which other files are close to this one, other items. So this is another one. Similar one would be a private keyword search. I have some keyword and I want to know what other texts also have my keyword or something which is similar to this. Private search is something which is really important today, because if I want to find out some information or anything which I want to look on the web, many times I still want to make sure that my information is private, whether it's for medical purposes, whether it's for, if it's stock market options or anything which I still want to find out information, but still to be private. Maybe last and maybe but not least, and talking to Krishna yesterday, so he told me about this other motivation for pattern matching. So this has been done mostly for DNA applications, but it could be for anything. It's not the same thing, but it's something also similar, that I have some substrings and you have, say, all of these long DNA genome sequences, and we just want to know what genome sequences have this substring inside them or something close to it up to some distortion. Great, so let me do a little bit of the math over here and to see what can be done over here. And so basically the scheme that we wanted to propose and to talk about is doing the same thing. So we said Alice is one of over here, and let's assume again, so all of these points are just like agents with locations. Alice has her own locations over here, and she wants to know what other agents are close to her in her neighborhood. But she doesn't want to expose her location. So what she can do, if we think about, we have multiple servers at this point, and then she can just choose some, with some randomness, some points, a point per server. So maybe she's using this, instead of her location, she's using another nearby location, and she's sending this location to one of the servers. And now she's going to ask the servers, tell me what agents are close to you up to some distance. So this server can reply, and we will increase the size of this radius in order to make sure that we still have a good value of privacy over here. So maybe this server would say, hey, all of these agents are close to me up to this distance. I don't talk here about how complicated it is to do that in terms of, so another dimension of the problem is how to do this task efficiently from the computational point of view, but this is outside of the scope of this part. Okay, so she's gone to the first server and then she asked for this one. Now she could do the same thing and she go to another server and choose another nearby point, not hers, and ask the same question. So given some radius, and then the second server will respond with this set of agents. So at this point, it's already good because now she can already restrict the close agents to be the intersection between these two balls. So now she can continue. She'll do the same thing for a third one, and then she get another one, and we can restrict even further. So now the intersection will be only this part over here. So you want to continue doing that while making sure that the intersection, ideally the intersection would be exactly the ball that you started with, say like a radius 5 over here. So it really depends how many servers we have, what radius we choose, which will affect also the privacy. So, but this is basically what the problem becomes, is how can we actually bound almost exactly or very close this ball over here with some other bigger balls that we can send as queries to the other servers. So just to be formal over here, so she choose some points with some radius per point, and the radius would be usually larger than the radius that she wants to start with. And then every server responds with a list of all the agents that are close with respect to the point that he got. And eventually, Alice needs to take the intersection of all indices of all the agents and conclude that these are the ones that are close to her. Great. So now let's say that I want to achieve zero distortion. So I want to make sure that Alice will get exactly all the agents of distance at most 5 from her location. I want to get exactly this one. So actually, one solution to do that, she wants to be at distance at most 5, but let's say that we'll take another sphere over here of distance exactly, say, 10. And what she can do is she'll take one of the points of this shell, of this sphere, and then she'll ask, we'll do the same thing. We'll send this location to the first server with an appropriate radius, and then we get an answer. Now she can do the same thing for another point on the same sphere, and so on. But we'll need like many points because every point basically means a server, so that's a little bit expensive here, but it's something which we do. So if you do the same thing, and I'll take basically all the points on this sphere of radius, say 10, and now what we can do is to take the ball around every point over here. And you can do that, and you can see every time, if we make sure that the radius is large enough. So basically the radius of this point would be, if this is S, it would be basically the sum of the radiuses that you want, like the 5 plus 10. So it has to be relatively large. But if you do that, no matter how many times you're going to intersect, you're still going to get the ball of radius 5, which is good. If you take all of them, you get exactly. So you don't get anything from the leftover, from the sides over here. So this is good. So now she can do the same thing for all the points, and eventually she's going to get exactly the ball that you wanted to start for radius 5. You get 0 distortion. This is all great, but the problem is that you need to have a large number of servers. So L is the size of the file, say number of bits, 1 million bits or even more, and S is the radius that we chose for over here for the bigger shell. So it's going to be many servers. So this is not practical. And really the question is, can we do better than this? Can you choose a smaller set, fewer number of points on this shell over here, such that the intersection will still be, I want to make sure that everything is going to be 0 distortion. So the question is, can we do that? Can I find a set of points on this sphere over here, such that if we'll take their intersection, so maybe instead of choosing all of them, I'll use only 6 or 7 over here that I have. And then we'll draw all the balls comparing to these points. And we still want to make sure that eventually the intersection of all of these balls will be exactly the ball of radius 5 for Alice. So this is basically, becomes like a nice design combinatorial problem in the sense of really bounding this. And we want this set, Z, to be as small as possible because the size of this set tells you exactly how many servers you need to have. And usually it's not an infinite number. It's something which we want to restrict. So this becomes a nice problem that we want to study over here. And basically the problem it goes as follows. L would be the size of the file, so whether it's 1 million or even more than that. S and R are the radiuses that we want. R is, say, 5 for the radius of Alice. S is 10 for what we go on the shell. And epsilon is the distortion. So we want to make sure that the intersection will include the ball of radius 5, and will not be too much. So maybe we're going to get some other agents of radius of distance, say 6, 7, but not 8 and above. So that's basically what we want to have. And once you find such a good set, so of points over this sphere over here, the idea is to use this protocol and take every point sent to one of the servers, choose the radius, and then continue and eventually getting the intersection of all the agents. And the question is now, what is the best distortion we can do? Ideally, we want to have the distortion to be 0, but clearly it's a trade-off. If we're going to have many more servers, then the distortion will be smaller, and the other way around. The privacy is something which we have to be careful over here. But in terms of vectors and binary vectors over here, what we can do, first of all, is just permute all the indices of the locations of the files. And then when a server gets a file, say now it's going to be of a Hamming weight S, then it means that the location of Alice could be any other vectors of weight at most S from the location that he got. So that basically tells you what would be the privacy level. And again, it's not possible to achieve full privacy over here, but you want to get as close as possible to 1. Okay, so I'll skip like some part of the math or something, but I'll tell you some of the highlights and ideas. So it really depends. S is the bigger sphere, as I said, and R is 5. S, for example, is 10. And so one of the things which is possible to show over here that if S is not too large, if we don't require like a high level of privacy, the number of servers we need to use is relatively modest. It's like R plus 3. And that, for example, will tell you, even like the construction is relatively simple because it tells you exactly how to construct the set Z that guarantees this zero distortion. So again, so this is basically the vector. You want to choose R plus 3 vectors for this set Z, and then set L plus or R plus 3, L over R plus 3 ones in each one of the vectors. And again, eventually you're going to get this structure over here. So the intersection is going to be exactly this set. This is strictly optimal, so in terms of lower and upper bound. The question becomes more interesting. What happens if the value of S, if I want to have a larger value of privacy? So N's, whether it's 0 distortion or higher distortion, what should be the number of servers that we need to use? So we have some result. I'll skip like the formulas and everything, but it's basically increasing the value of S that we can guarantee in terms of the privacy, and then starting an upper bound and lower bound in terms of the number of servers that we need to have. So again, like I'm skipping some of the details over here, but I'll just tell you that it's interesting to study over here upper and lower bounds from the theoretical point of view, as well as constructions, extension for colluding servers or other setups, whether it's not necessarily just the Hamming distance. So you can think about any distance measure that you want to have and having similar construction for this. So this is some of the plots in terms of here for upper and lower bound for 0 distortion or for example, this is distortion 2. And just so that, do I have time until 10 or? What is it? Until 10? Or? Oh. 10? Okay, great. Great. So, okay, sure. Okay, so in that case, I'll spend another 5 or 10 minutes for. So this is basically closes like the first part, the second part, which I want to talk about. So maybe the last part, if I have 10 more minutes to talk about, it's another joint work that we had with Moshe, and I'll go back again to the first setup that we had for the private information which we have with a fairly first and simple example. And we say that, so this is almost like done at this point. If we have 2 copies for the servers and we have the database, so this is all good. We can ask the queries, and then we say we only need to download 1 file per server. So the problem is solved, it's done. However, it's not necessarily, because if, let's say that you have 1 million files, and every file is 1 gig, and you send some random vector A to one of the files, and then the file needs to take the sum of all the files which have indices 1. So, and it's a random vector, so roughly half of the bits are going to be 1. So actually, to compute this part, the inner product between the binary vectors and the database, that's expensive, because you have, on average, you need to go over half of the files. If you have 1 million files and each file is 1 gig, that takes a lot of time. So that would take much more time than the download that you just need to transmit the file. So what actually becomes the bottleneck at this point, it's not the upload, neither upload nor the download, it's basically the computation. Is how do we actually compute this part over here, and how to do that efficiently. So it's also, I mean, you can sacrifice the privacy over here. Instead of just using just like a random vector, maybe I'll use a random vector which is low weight. Because if it's low weight, then it means that the server needs to access a fewer number of records, of items and files. That would be great, and then you sacrifice the privacy. And that's a legitimate trade-off to do. The question is, can we do better? And can we do better from the sense of point of, let's say I still want to be fully private, for example, but I want to make sure that the computation will be done much faster. And one way to do that would be to adding some more files to the servers such that you can compute this part more efficiently. And this is what we wanted to study over here. And I said, so this is a joint work together with Moshe. And so basically what we have is the server receives, again, like this random vector, and he wants to compute the inner product with all the files. And in terms of how many files the server needs to read, so on average we said it's a n over 2. Worst case could be even like n files, because A is a random vector. Great, so now what we define here is the access complexity. It's the number of files the server needs to read, either worst or average case. And this problem is actually interesting for PIR, but not only for PIR. Everything which you need to compute over the server, you need to send something, and you want the server or anything to do something, it really depends how long the computation is going to take. And the question is, can we do some coding setup in order to improve the computation part? So can I compute something in advance before that, such that whenever I'm going to get this random vector A, it will be possible to read a fewer number of files in order to answer the query from the user. So that's basically what we wanted to study here, how to improve the access complexity. And let's do like one simple example. Let's say I'm going to have one more file that is just going to store the sum of all other files. So if Alice is going to send some random vector, and if the weight of the random vector is at most half of the size of the vector, then it's great. So the server can just respond directly, because the number of files he needs to read is at most 1/2. Great. But if the weight of the arbitrary vector is larger than 1/2, then because we have this other file, which is the sum of all of them, so instead of reading this file, you can just read the complement. You can read all other files and just XOR this with the sum of all the files that we already stored from the beginning. So in this case, no matter what happens in terms of worst case, the number of files the server needs to read is at most 1/2. If you think about average, if n is relatively large, it still remains n over 2. So it doesn't necessarily improve on that. But it's an interesting question to see how to improve both on the worst and the average case. So basically this problem of PIR, and again other problems, could have now 3 dimensions, 3 trade-offs. One we said is this PIR rate. PIR rate is the ratio between the size of the file and how many files we need to download. The storage overhead is how much we store, and that could be both for the coded setup if we store the file using any kind of code over the servers, or how much of the extra redundancy I have I'm going to use in order to improve the access complexity. So it's not only working over here on this edge, now we want to work over this complete area over here. So we need to study all trade-off between PIR rate, access complexity, and storage overhead. So I'll tell you some of the ideas how to do that. And so let's say again, going to this example where she's going to send like some random vector to one of the servers, and the server needs to respond to compute this function over here. And we want to improve the access complexity. So one idea is to, if I'm going to take the database, which has n files, we want to encode them into a larger number of files. And you want to do it in a way that whenever we need to compute a times x, we will be able to do that more efficiently. And how to do that more efficiently, what we want to compute eventually is, I'll go over here, is a times x. Now we're going to use what's called a covering code, and we want to use some, basically some code over here, and this is what's they call a parity check matrix of the code. And we want to find some vector e that if we multiply by the matrix h, you get exactly the random vector that Alice wanted to send. And once you have this property in hand, and I'm skipping again the details, but once you have this property in hand, instead of computing a times x, you can just take the vector e, which is close enough by what's called the syndrome to this vector a, and then compute only this set of files that will give you exactly this property, h times e equal to a. So this is what's called a covering code, and that's the property that we wanted to use over here to make sure that for every code, every word in the space, you have a code word which is relatively close to it. And once you have a covering code, then you can use this one in order to build a scheme in order to improve the access complexity, but again, both for PR and any other application. Okay, so if you want to put everything together here, you take the database, you encode it using this covering code, and once you have the covering code and you store everything, whenever we get this computation that we want to have, then we can do it more efficiently. The question is, again, like what's the trade-off? Well, because using a covering code, using a code, that costs you in terms of storage overhead. And so the question now is, what's the relation between the storage overhead that we store in the server, we have some extras, to how much we improve in the access complexity. So there is some, basically some part how well you can do using a covering code and how that improves you in terms of the access complexity. And that's basically the plot over here. So the storage overhead is how much we had to pay extra on top of the database. So maybe a factor of 1.5, 2, or 3. And then the access rate is how much we had to, a ratio of the number of files that we needed to read. And we want to improve from 0.5. I mean, you can go as down as you want, but clearly you have to pay in the storage overhead over here. So I'll just tell you some of the part which is still left open over here as a work in progress. And the question, this works for the worst case. How to do average case is still something which we still struggle with, but it's a good problem. And also, if you want to have some MDS code or other PR setups, in many other setups of PR, you don't just get like one query. You're going to get like maybe 2 or 3 or even more queries. And then the question is, if I'm going to have multiple queries, how can you do that? I mean, I can do the access complexity per query. But the question is, can we take all queries together and find a scheme that works for that? And that's another challenge. So I'm skipping the details just for the sake of time that I don't go over time. But so basically, what we want to study over here is the connection between the access rate and what happens if you have multiple requests. Last but not least here, it's also, let's say that I'm going to have three servers, how do you allocate the storage? So this is really working on this the 3 dimension of the problem. If I'm going to have 3 servers and every server can store a database, you can use it, first of all, you can do coded setup over the servers just to store the file, but you can allocate part of the server just for the access complexity. And it's a good thing to see how to do this allocation. How much of the server do you allocate just for to store in that using, say, an MDS code? And how much do you actually allocate for the server just to improve the access complexity? Okay, so let me wrap up and just to tell you what we discussed. So it's really, we started with this PR model that this problem has been studied for both from the CS and the information theory point of view. And again, it's a hot topic from the IT community. And one of the dimensions that we're currently working on this, what we call this private proximity retrieval. But I think in general, it's an interesting problem to take any information retrieval problem that you currently have, not just asking for a file or something only for every information retrieval problem that you want to have, and just add the word privately before that, and then it becomes an interesting problem to see how to do any information retrieval problem with privacy. And again, the access complexity, I find it to be interesting not only for PR, but any kind of computation that we want to have. And again, there are many more other open problems, and I think it's a good time to say thank you and to see if you have any private queries. It's a good question. I think it's a matter of the distance metric. Oh, sure. So the question is going over here for this private proximity retrieval. So Tzachi asked whether balls are really the best structure that you want to have. Maybe you can use like a elliptoid or ellipse instead of using like a ball or a cube. I mean, you can think about any other geometric structure that you want to have. Intuitively, I think balls are optimal. I mean, if you send some other information, I mean, even if it's a cube, it becomes a ball if it's a Hamming metric, for example. But it's a matter of how also like a matter of privacy, because if I take an ellipse, then I need to have like 2 points for the centers that I need to transmit. So I want to be very careful with the privacy that I want to protect. And this is why a ball is like, I'm just sending like 1 point and the radius. So for me, intuitively, I think a ball could be optimal, but again, like it's not that we prove that. Again? Yeah, so basically, if we work over a cube in the Hamming distance, the cube it's also a ball because you said this is the center and that's the radius, so it's the same concept. So the question is, can we do something which is active? So for example, in the private proximity or any other PR setup, I'm sending the first query to the first server, and based on this, I will continue in asking the following queries. So this has been studied by Sunan Jafar of this multi-round PIR. You could also do it, say, over here and decide based on that. So we didn't explore this, but it's definitely a good idea, especially for this with locations and distances. So maybe that gives you a better way how to ask the following questions. But yeah. So basically, if I'm trying to summarize the question is, there is one part is, can we do like a third party that both the user and the servers protect? And just for that part at least, so some of, even like this private proximity retrieval or talking about the locations, many of the solutions do assume that you have a third party that both of them trust, and then they both communicate through the third party, and then having solution there this way. But we want to bypass this third party and to do that. For the second part, talking about the index coding, I completely agree that this problem falls, it's similar to this index coding that you want to ask some queries, some points, and based on that to decide. We didn't find a direct connection. We're trying to see what combinatorial problem it's completely kind of like related or maybe even like fully solved, but we didn't see anything of it. Yeah, I'll repeat the question. Chaim asked whether it's related in any way to blockchain. So I think the short answer that I don't know, because I'm not an expert on blockchain. But maybe I think it's a good marketing for this talk, because once you say blockchain for anything today, then people will actually read it. So then I would say the other short answer is that, yeah, it's completely related to blockchain. the PIR and the, okay. Okay. Uh, this one? Mm-hmm. Not, maybe I'll go over here. Um, so the syndrome is going to be this request A. And you want for every syndrome, which is the request, to find a code word such that if you multiply the syndrome of this code word would be exactly this syndrome A that you want to have. So it's basically, I mean, you want to find another error vector. If you multiply by the parity check matrix, you get exactly the syndrome. And you want this error vector be of low weight. So if I have this property in hand, once you get request vector A, you want to find the error vector. This is guaranteed by the covering radius that you want to have, such that if you multiply the error vector by the matrix, you get this is the syndrome that you want to get. And that's what you guaranteed from having the covering code. And once you have this, when you want to multiply A times X, now you can replace A by H times the error vector. And instead of reading the entries corresponding to the vector A, you just need to read the entries, the encoded files, which are reflected by the error vector that you want to have. So this is basically the property over here. So just to take in like off the shelf any linear covering code and use it over here. Yeah. So the question is for the PR rate. Maybe I'll go. They can work it. One by one, yeah. Yeah. So I'll go over here, and the question is about whether MDS codes are optimal in order to improve the PR rate. And I think it's not fully known. Like it's most of the setups, they use MDS code, and then they show that indeed they know what the PR capacity is. So they say, but it's kind of like, okay, it's the chicken and egg. So when they calculate the PR capacity, they do it for an MDS setup. So the interesting question is to say that you have a storage overhead, storage rate that you can use. What is the best code that you can do in order to have, so I think this is not fully solved. And maybe you know better than me about this, or no? So this is not fully solved at this point, yeah. So my conjecture, I guess, is that the MDS is optimal, but but they do have some other examples of non-MDS codes, LRC or some other ones, that also achieve the PR capacity. Yeah. Thank you.